So today we're dealing with these reciprocal functions that look a bit more complicated. For this one, and actually most of these, the first thing you want to do is actually simplify it. So step one in being able to graph it is to simplify. And simplifying these, remember, it's got a quadratic in it. I want to factor that quadratic. And so if I factor that quadratic, in this case the denominator, notice it gives me x plus 5, x minus 3. That's very useful as it turns out, because you'll notice that I do have something I can cancel out of both top and bottom. I can cancel this x minus 3 out from both. Now if I do that, what's left on the top? 1, absolutely. And so really this equation simplifies down to just be y equals 1 over x plus 5. So that's really what we're going to be graphing. However, we do need to think about our restrictions. In this particular problem, what can x not equal? Well, of course, in the final answer, we see that it can't equal negative 5. But remember that the restrictions are anything that would ever have made the denominator equal 0. So it's both the negative 5 and the positive 3. Now that's going to end up being important information as we go forward on this one. So make sure you have that noted on your paper, that this whole thing, including the restriction, is what it simplifies to. All right, so from here, let's go ahead and start making our graph. And we're going to see how we end up using this new information here in a moment. But first, we can go ahead and just make the graph of y equals 1 over x plus 5 like we normally would. What does the plus 5 do to our graph? Yep, shifts it left 5. And so the first thing I do is I draw in my asymptotes, and the only thing that's changed is that it's been moved left 5. And then for making my graph, it's the same sort of thing as normal. My first point, that's going to be over 1 up 1. And then I can get more points in. So for instance, I might choose to go over 2. And if I go over 2, that means I go up a half, because 1 over 2. Notice it's all relative to where those asymptotes intersect. Or I could go over 3 and up a third, or over 4 and up a fourth, or I'll actually go over 5 and up a fifth, just because it's a little bit further out, might make me a little bit more accurate. And I can do the same thing going over a half, going up 2, or going over a fifth and up 5. But notice the symmetry here. These points are symmetrical with these points. So once you find that set, you can find the other as well. That lets you get those points in. Repeat the process in the bottom left as well. Down there we go left 1 and down 1. And then again, for instance, over 2, down a half, over 5, down a fifth, all that kind of stuff. Now I've plotted enough points, 5 in each of those quadrants, to be able to have a pretty decent idea about what the curve is going to look like, so go ahead and draw the curve in. And now we see the point where we have to now deal with our restrictions down here, because earlier when we simplified it, we found that x cannot equal negative 5 and 3. Well, notice we've already dealt with one of those by drawing in the asymptote. The asymptote is at negative 5. And so by drawing in that dotted line, I accounted for that. But what about the 3? Over here at 3, where x is 3, I shouldn't have any graph there, because x cannot equal 3. If I plugged in 3 up in the original equation, it would give me undefined, remember. And so what do I do about that? This is where we actually make our graph, and then we do it in pencil so we can erase that little spot, and we draw in an open circle where the graph crosses x equals 3. So anything that you list as a restriction, it has to show up in the graph either as an asymptote as the -5 did in this case, or as a hole in the graph. And yes, that's actually how we reference it. We just call it a hole in the graph, represented by an open dot at that point. Now, having seen the graph, let's take a look at what the domain and range would then be for a graph that looks like this. Well, domain, of course, remember, that's our x values. And so, in this particular graph, remember, we've always just said it was x cannot equal the asymptote. So we before would have said just x cannot equal -5. It's all real numbers except for -5. But in this case, we have one other number to worry about. We also have the hole in the graph. At that point, that can also not be part of our domain. And so my domain is actually x cannot equal -5 and 3. Notice the restrictions. It's the same as the restrictions. Because really, restrictions are specifically, if we set it out the long way every time, we'd say these are the restrictions on the domain. Now let's go to range. Range, of course, is talking about our y value. And we know that y cannot equal 0 because that's where the asymptote is. But we do run into one other issue here. There's also some y value at this hole that we need to account for. Because if I look all the way across at that hole, which is just a little bit above my asymptote, but if I look straight across that line that goes through the hole, it never hits the graph anywhere else. So there's some value there that also is not going to be part of our range. And we need to know what that is. Well, we can actually figure it out from our simplified equation. Remember that we know that y equals 1 over x plus 5. Except for where x is 3. But if I plug the 3 into this, y equals 1 over 3 plus 5, I would get y equals 1 over 8. Now, if I plug that into the original equation, it's going to tell me undefined. But by plugging it into the simplified equation, it actually tells me where the hole is. So it tells me then that this point right here, the coordinates are 3, 1/8. Which means that this 3 is not part of the domain, and this 1/8 is not part of my range. And so I would actually say that the range is y cannot equal 0, the asymptote, and 1/8, the hole. So now we go on to this problem, which looks even more complicated than that last one did. But our basic idea behind it is going to be the same, where we're going to want to start by simplifying this equation as much as we possibly can. So then that means that on the right side, I'm going to have to do that division. Step 1 with doing that division, I like to factor first. And so the one part that I could factor here is the x squared minus 1, because that actually equals x minus 1, x plus 1. Now, having factored, I can go ahead and do the division aspect. Remember, in order to divide fractions, we flip and multiply. That is, multiply by the reciprocal. And so I flip the second fraction and change the division to multiplication, always in the same step. That's not two separate steps, that's got to be one single step. And then I can go ahead and multiply those into a single fraction. And now that it's a single fraction, I can look and see what can I cancel out from both top and bottom, because everything's factored. So if there's a factor in the top and a factor in the bottom, I can cancel them out with each other. So the x plus 1, yes, there is one of those that I can cancel out of both top and bottom. The x minus 2, yes, I can cancel one of those out of both top and bottom. Notice what that leaves me with. That leaves me with nothing on the top. Specifically, actually, though, that means there's going to be a 1 on the top, because we're dividing it by itself. And on the bottom, we're going to have x minus 1. So this is actually what that whole big original equation actually looks like when we simplify it down. Much easier to graph, thankfully, purposefully even. But we do need to now account for the restrictions. So we need to say what x cannot equal here. Well, remember that x cannot equal anything that was ever going to make the denominator equal 0. Well, if I take a look at this step, this is the one I tend to look at first. So looking at that step, that's going to tell me a positive 2, a positive 1, and a negative 1. Because all of those would make that denominator equal 0. Okay, now I'm going to continue looking up and see if there's any that I haven't just accounted for. So in this step, all the same. In this step, before I flipped them, it just happened that both of them were x minus 2, so I actually have accounted for that already. And up here, they're still both x minus 2, so everything's now accounted for. So those are my restrictions. Make sure you have those written down with your equation, and that you've written down the simplified equation, because we're going to be using this now going forward. So now that it's time to make the graph, we're really graphing this. Y equals 1 over x minus 1. Well, the only transformation here is the minus 1. And so the parallel transformation, that's just going to be the 1 over still. The transformations, it's going right 1. And because it's going to have asymptotes at x equals 1 and 0. And once I know that, the very first thing I do is draw those asymptotes on my graph. And having drawn the asymptotes, we can now go ahead and make the graph. So the first point goes over 1, up 1. And then I chose to go over 2, up a half, over 5, up a fifth. But again, that's just what I'm choosing to do. You could go over 3, up a third, or you could go over 10, or, well, over 9 at least in this case, and up a ninth, or whatever. Do the same thing in the bottom left. Over 1, down 1. And then, like, over 2, down a half, and so on. And then you can draw in your curve. But we're always doing it in pencil because we know that there's going to be a little bit of changes to make to this one. Because remember, we had restrictions in this equation. We were told earlier, or we found earlier, that x cannot equal 2, 1, and negative 1. Each of those is going to have to be accounted for in this graph in some way. So the 2, well, at x equals 2, right over here, it looks like I have a point there. I can't have a point there, so I'm going to have to erase that and replace it with an open circle. At 1, next, well, the 1 is where the asymptote is, so I've already accounted for that one. And then the negative 1, the negative 1, well, you notice at negative 1, again, looks like I have a point there. I'm going to have to erase that and replace it with an open circle. So by the time you put the holes in the graph, this is what your final product should be looking like. So now, as we take a look at the domain and range, again, the domain, that's just going to be the restriction. So remember, the domain, x cannot equal each of these places where we either had a hole or an asymptote. This should match up with the restrictions we found earlier. Every hole or asymptote should be part of the restrictions and therefore excluded from the domain. Then we take a look at the range. Range, of course, that y can't be. And again, it's anywhere where we have a hole or an asymptote. Now, the asymptote, we have to know the asymptote by being able to look at a graph. We have to know that by knowing how far the graph was shifted up or down. So that part tells us the 0 that's going to be over here. But the holes, well, we have to do a little bit more work for the holes. And in this particular option, because it actually is doable this way, you have 2 options. One option is now take the 2, the x value of that hole, and the negative 1, the x value of that hole, and plug each into our simplified equation. Or, well, remember how we plotted these points? We can actually know exactly where they were, because remember, to get this point, when I was first making my graph, that was over 1 and up 1 from my asymptotes. So that's got to be up at 1. And this hole down here, well, that's the one that I got by going left 2 and down a half. So I can actually know that that one is going to be at a half for that reason. Negative 1/2, actually, to be specific. And so we can know those just by looking at the graph that we made. But again, if you didn't have your graph set up in such a way that you could just look at it and know, or if the numbers were harder to read, they're further out, something like that, yes, you can always plug these values into your simplified equation to find out where those holes would be.